Today we're introducing quadratic functions. So we're going to start with the form of f of x equals ax squared plus c. Quadratic function is a function that can be written in the form of f of x equals ax squared plus bx plus c. A, b, and c have to be real numbers. And the form where it is in ax squared plus bx plus c, it's the standard form of a quadratic function. So when you are graphing quadratic functions, you need to find at least 5 ordered pairs that satisfy the function. And then you plot those ordered pairs on a coordinate plane. And then you connect those ordered pairs with a smooth curve. So for our first example, we'll make a table for the function. And our function is f of x equals x squared. So this is the parent function for a quadratic function. So we'll start with 0, which gives us 0, 1, which gives us 1, negative 1, which gives us 1, 2, which gives us 4, and negative 2, which gives us 4 as well. So then we will look at another quadratic function. This one is 3 times x squared. So when we plug in 0, we get 0. When we plug in 1, we get 3. When we plug in negative 1, we get 3. When we plug in 2, we get 12. When we plug in negative 2, we get 12. Make sure that when you're plugging values in, that you are squaring them first and then multiplying by 3. Alright, so we're going to plot these two graphs. So if you notice, the blue graph is the x squared function. And then the red graph here is the 3x squared function. So notice that each point on the red graph is 3 times higher than the corresponding point on the blue graph. All right. And so because it is 3 times, it makes the graph of g of x, which was the 3x squared, it makes it appear a little bit more steeper or more narrow than the graph of x squared. And remember, x squared is our parent graph, and then 3x squared has an a value of 3, and because it has that value of 3, it became more steeper or more narrow than the parent graph. Alright, let's look at example 2. We have our two functions here. We have p of x equals negative x squared and q of x equals 1/2 x squared. So first we'll make some tables. We'll keep our values 0, 1, negative 1, 2, and 2 for our x values. So when we plug them into that first function, p of x, which is the negative x squared, make sure that you're squaring your values first and then applying the negative. So we get 0, negative 1, negative 1, negative 4, and negative 4. And then we'll look at the next function, the q of x, which is the 1/2 x squared. Make sure you're squaring your x value first and then taking half of it. So we get 0, 1/2, 1/2, 2, and 2. Alright, so the shapes that our graphs are making, we call them parabolas. So parabola is the shape that a quadratic function makes. And that turning point of that parabola is called the vertex of the function. So the vertex is either going to be the lowest, which is the minimum, or the highest, which is the maximum point on the graph. So the parabolas in examples 1 and in example 2, they're all symmetric across the y-axis. So that y-axis, or where it's folding over and then symmetric, is called the line of symmetry. So we notice that when we put a 3 in front of the x squared, it became more narrow. And then when we put a negative in front of the x squared, it flipped it over and everything flipped downwards. So we can say that if the a value has an effect on our graph. If our a value is positive, the graph is going to open upward. If the a value is negative, the graph is going to open downward. If our a value is greater than 1, then the graph is going to be steeper. If the a value is less than 1, the graph is going to be flatter. Alright, so we'll graph some more and compare. So we have our x squared, and we have x squared plus 2. So we'll get our values on our table. Okay, and so when we compare those two graphs, we have our parent function, the f of x equals x squared in black, and then we have x squared plus 2 in green. And so notice that each point is 2 units above the corresponding point on the parent function. So the x squared plus 2 is a translation of the parent function. It's a translation of 2 units up. Alright, so we'll graph some more. We have this 3x squared that we did before, and we're going to compare it to the 3x squared minus 4. So we'll go ahead and get our values for that on our table. Then we'll put points. And so you'll notice that our original graph, which was the 3x squared, compared to our new graph of 3x squared minus 4, it looks like everything on that new function, which is s of x, that s of x equals 3x squared minus 4, all of those points are 4 points below the corresponding point on the g of x equals 3x squared function. So the graph of s of x is the result of translating the graph of g of x 4 units down. So as you can see, adding a constant to our quadratic function has an effect on the graph. If our c is positive, the graph slides up c unit, and if our c is negative, the graph slides down c units. And then also we know that our vertex, which is either going to be the minimum or maximum, is going to be at 0, whatever that constant is.